Hi everyone, my name is Brian Dadahong. I'm a student of Electronic System Engineering in MJIIT, and my final year project is titled Task Allocation for LoRa in Provision of Wellhead Growth and Tilt Measurement Services with Reinforcement Learning, and my supervisor is Dr. Zool. As an introduction, Malaysia is rich in oil and petrol. There are many offshore oil stations stationed around Malaysia's seas, oceans. As you can see from the photo, they are usually situated at the middle of, I would say, most likely like nowhere. And for this FYP, if you just zoom at the almost at the bottom of the station, you will notice they will use a structure called Wellhead, where they will drill the petrol from the seabed. And as you can see from the image, as the procedure going on, you will notice the wellhead will have tilt, and this will cause trouble for the engineers on board, and thus they need a system to monitor this wellhead. Well, the challenge to fix a device on deck, there are a few to be named. Normally, like what I mentioned just now, all these oil stations will be offshore, and a set of safety precautions need to be taken. For example, we cannot just set up any electronic device which will use electricity on deck without permission from the engineers on deck. This may seem like a standard procedure, but as an electronic system engineering student, I understand that if every time we have to apply permission to set up a new device, it will be quite headache, as we will have many LoRa devices to be set up on deck. And next, since it's located almost in the middle of nowhere, there will be limited internet access from the deck. And thus, if let's say I were to set up my device on the deck, that means I have limited access to the device unless I go stay on the deck. So right now, you may ask, what are the suggested methods to transmit the data in the deck? Well, for my FYP, I've decided to use LoRa to transmit the data. LoRa is well known for its long range capability to transmit data. But however, when we configure LoRa, there are a set of configuration that we may set, and it will all affect the performance and also the battery life, such as the spreading factor, the power set, and also frequency as well. So this is ultimately lead to my objective of my FYP. First, as you can see from the picture, different spreading factor will result in different energy and also different bit rate, and all these parameters are affected by each other. So as a mean of configuration, instead of just try and error, I will use reinforcement learning to determine the proper parameters for all the nodes. And for your information, usually on the offshore oil station, there will be at least up to 6 wellhead. That means I will require at least 6 nodes or even more. That's why I have decided to use the reinforcement learning to determine the proper parameter for all the nodes. Next, for my algorithm, I've decided to use proximal policy optimization, and I want to prove that this algorithm can be used in the use of reinforcement learning, especially in this case, which is to prove and to determine the proper parameter for LoRa node. As for my methodology, first, I will need to determine the reward functions. In terms of nodes, especially LoRa nodes, I will use the flag ACK and collision. ACK is a short form for acknowledgement. In LoRa term, ACK flag is a part of LoRa 1 frame header. If the ACK flag is set to 1, that means the sender indicates that it has received a message requiring acknowledgement and hereby providing the acknowledgement or confirmation. Or in simpler words, it means that it has successfully transmitted a packet or a data. Whereas for collisions in LoRa, frame collision happens when two or more packets overlap in time and use the same LoRa parameter. For example, like what I said just now, the same spreading factor, bandwidth, or even frequency as well. As a conclusion, any packet that's sent within LoRa in any node that with ACK flag equal to 1 and no collisions, it will consider as a good data being sent. As for the algorithm, I've decided to use proximal policy optimization, which is known as PPO. PPO is an on-policy learning algorithm. It is known to be used to learn behavior in an difficult situation, such as like game playing, and also let's say a robot learn to walk. As for my configuration, I've decided to use CUDA as well to accelerate my speed during training. CUDA is a NVIDIA library which uses GPU to train AI. And also due to the many nodes, I've decided to use multi-agent reinforcement learning as well. As shown from the picture, this is the flowchart for the library which I'm going to use later, which is known as RAY or Reinforcement Learning Library. As you can see from the trainer, it will implement multi-GPU learner, and from that, it will send synchronous broadcast on new weight to the rollout workers, and then thus you'll have synchronous sampling and get sample batches, and this is how the training process works. This will be the simulation parameter which I'm going to implement. Here I have defined 100 nodes and also 100 intelligent nodes. The meaning of intelligent nodes is it will have the ability to decide its own separating factor or power set or frequency, which in this case is the thing that I want to manipulate. And then I will set one base station, which is the data which gonna send the destination of the data. And next, I will set initial as equal to random, which means all the nodes will be distributed in random manner. Next will be the radius. The overall nodes will be distributed across in a 4.5 km radius. Next, the packet length which I've choose is 50. And next, the set of spreading factor which I'm gonna try is a list consists of 7, 8, 9, 10, 11, and 12. And for this FYP, I've decided to set constant for my frequency and my power set. This is the flowchart of my overall coding. First, I'm going to declare my simulation parameter and also action set, which I just showed just now. Next, I also need to create a custom multi-agent reinforcement learning environment from the action set. Next, I'm going to generate the distribution of random LoRa nodes. Then I'm going to start the training. And when the training starts, the library will create training environment, a working training environment based on the number of nodes. For this FYP, I have decided my iteration will be 20. So for each iteration, first, the PPO policy will choose an action based on its policy and also the action set. Next, it will transmit the packet for each node. And of course, each node is being configured with the action set, in which in this case will be the spreading factor. Next, it will check the node status on the SCK flag and collisions. So, if the node SCK is equal to 1 and is not collisions, the reward will be equal to 1, and otherwise, the record will be equal to 0. If the whole episode is done, then it will run the second iteration until it runs to the final iteration, which in my case will be 20. And this is my result. After around 20 iterations run in Ray LIB, which took me about 45 minutes, as you can see, the total or the max reward for each episode is residing as 100 because there are 100 nodes, and each node result in a good packet, which it means it has successfully determined the correct parameter for each node. As a conclusion, PPO works in task allocation in LoRa, and simulation is done with 100 nodes. For future improvement, more actions such as frequency and power set can be implemented in the PPO as well. And that's all for my presentation. Thank you.